today we want to continue the Minimax theory, maybe finish it up, hopefully. Just to review, last time we said that this lower bound could be, that this minimax risk could be lower bounded by taking a finite set of distributions, so this is P1 to Pn, making sure that each of these is some minimum distance apart, s, in terms of this distance. And then we saw that that's bigger than or equal to, therefore, s over 2 times the inf over all psi, the maximum of Pj, times the probability that psi is not equal to j. That was our fundamental lower bound. Pick a finite set with some separation, and now we just have to find the maximum error probability of a selector. And last time what we did was the Lecombe's lemma, which is just this theorem restricted to the case where there was two distributions, which led to the bound times the Kullback-Leibler distance that was our fundamental lower bound. And this was basically up to a constant s as long as we chose to be. Okay, so that pretty much summarizes. This always means I'm leaving out constants like s over 2 and so on. Find two distributions that are about 1 over n apart in KL distance. Figure out how far apart they are in terms of the parameter values. And now you have a minimax lower bound. Okay, any questions about Lecombe's lemma before I do the next version? Yeah.
So it seems like in some spaces of probability distributions, it's not trivial to find two distributions that are that distance apart.
Well, finding them is usually not so hard. The question is whether it's giving a tight bound or not, which it may not be.
Is there a general rule for finding two distributions that are both not expected? If they're Gaussian, it's easy, but not.
No, it can be a bit of a struggle. It might be obvious. It might take some fooling around. It might be very difficult. Yeah. Unfortunately, there's no algorithm for this. This has to be treated on a problem-by-problem basis. We'll do the parametric case, and there it's pretty easy. You just pick one parameter and take a second parameter that's close to it, and that's it. And so we'll see that. However, there are lots of cases where this doesn't provide a tight lower bound. It's just the number is too small. Remember, we're trying to get, just to remind you, we're bounding the minimax risk by this lower bound we're using by this method and this upper bound. And it's easy to get some sort of lower and upper bound, but they're too far apart, it's not useful. And sometimes this just doesn't work with two distributions. We'll see an example in a minute. Well, actually, it's the one we've been talking about through most of the course, which is looking at the L2 error of a density estimator or a regression estimator, things like that. This method doesn't provide a tight enough bound. So that's why we need to use more than one distribution. And so now we're going to do the same thing for more than one distribution. The key is that we need to bound, again, this quantity. And there's several ways to do it. I want to mention two. I won't go through the proofs because they're like more elaborate version of the proof for two cases, but I want to say what the results are and how you use them. And one of them is older and one of them is newer, and they're very similar. So the first one is called Fano's method. It comes from actually a theorem in information theory called Fano's lemma, which says that, let's just look at this error probability, that if I have, let's just abstract the problem. I have x1 to xn from P, where P is some finite set of distributions. And again, the problem is simply to guess, is to do a selection, just to guess which one produced it. That's what we're trying to bound. We did that using that kind of Neyman Pearson argument here. Fano's lemma just generalizes that, it just says that the maximum over J of the probability that any selector, give me any selector, what's the probability it screws up? I actually called that Z in the notes. Just to be consistent with last day, I'll call it psi. It's the same thing. Okay, psi and Z are the same thing. And we use the same trick. The maximum is bigger than the average. And so now we've just reduced it to the following problem. I generate an observation. You guess which distribution it came from. What's the probability you make an error averaged over all the distributions? And Fano's inequality, but the proof is in the appendix, says that it's this. It's 1 minus n beta plus log 2 all over log n, where beta is equal to the maximum of the Kullback-Leibler distance between each pair of distributions. See, in Fano's inequality, we ended up with just the Kullback-Leibler distance between two of them. Now we have to look at all of them. Okay, so let's see how we use this. So the proof, again, it's not so difficult. It's a generalization of the proof we did for 2. It's in the appendix if you would like to see it. But I would like to concentrate on how we actually use this. But what we have to do, by the way, when I combine this with the thing out front, that gives me a bound on the risk. The risk is bigger than S over 2 times this quantity. To make this useful, we have to make sure that this thing is not going to 0. Otherwise, we wouldn't have a good bound. So let's try to make it, say, bigger than like a half. So if you choose these distributions, you're going to pick these. So remember, with 2 distributions, we picked them how? So that that pair of distributions was Kullback-Leibler distance about 1 over n. Now we're going to pick it so that beta, this maximum distance, is less than or equal to this. So it's just like before, 1 over n, except now the log number of distributions comes in. And you can check, if I do that, that this is bigger than or equal to a half. I chose beta, so that this is bigger than or equal to half. So that gives me a lower bound of S over 4. So that's how you do Fano's inequality. Instead of picking 2 distributions now, we're going to pick n distributions. We're going to choose them so that the distance between any pair and Kullback-Leibler distance satisfies this inequality. We'll see how to do that in an example. And then you're done. You just say, what's the minimum distance? This S will now be the minimum distance between each pair. And that's your minimax bound. And so I'll show you how to do this in an example in a moment. I just want to see if what we have to do is clear. Any questions about that? This is Fano's method. Probably one of the most common ways of getting a minimax lower bound. Yeah, you don't want to use this for big n equals to 2. This is only going to help you when n is somewhat larger. Okay. So I want to now mention the next method, which is on page 9, called Sibikov's method. The only difference is this. Instead of this bound right here, Sibikov's method gives you a slightly tighter bound. And the condition you have to check is slightly easier. So Sibirkov's method I think of as sort of a sharpening of Fanel's method. It's more modern, but I would say to me it's the preferred method. If you're going to use Fanel, you can usually use Sibirkov's method. It's a bit easier. The only difference is this. You pick a P0 and then a P1 to Pn. So the way to think about this is, for doing regression, this is probably going to correspond to some centered thing like the zero function. And these are going to correspond to other regression functions that are little perturbations of that. So there's kind of a natural null guy here. And the condition you need is not that the maximum KL distance satisfies something, but rather that the average KL distance of Pj to P0 has to be sufficiently small. Actually, less than or equal to log n over, well, actually, the way I wrote it there, it says 16, but I think we really want, oh, no, that's right. I should have said, did I do the I just want to see if I did it for a single observation or n observations. Let's put an n here. So I don't have n in the notes. I did it for n equals to 1 in the notes. But in general, you can do this for little n observations. So in general, you're going to want this condition to be satisfied. Is that right? Actually, let me check. Hang on. Let me check that. Let's come back to that in a minute. Something's bothering me about that right now. N. We'll come back to that in a second. There may be an n missing. Let me check it. And then we get the same result, that it turns out that this is now bigger than or equal to, as it turns out, an eighth. Okay, so if this condition holds, then we get that the maximum over j, the probability that psi is not equal to j is bigger than an eighth. And so when we combine that with the s over 2 in front, we get that the minimax risk is bigger than or equal to s over 16. So to summarize, we pick now n plus 1 measures. Instead of checking the Kullback-Leibler distance between each pair, you check the Kullback-Leibler distance just between Pj and P0, this special guy. And you make that less than or equal to log n over, it's either 16 or 16n. I'll figure that out in a minute. And then you look at the minimal separation, s, and that's your minimax risk. It's bigger than s over 16. Yes?
What does it mean for P0 to be absolutely continuous with respect to each Pj?
That's a technical condition. It just means that whenever Pj puts 0 probability on something, so does P0. I don't know why I even put that in there. It's something that's always going to happen for our examples. Yeah. Okay, so I'm not going to go through the proof again because it's quite a bit longer than the Lacombe proof we did. I mean, it's similar in spirit. There's like essentially constructing like a likelihood ratio test, summing things up. It's very similar to what we did, but now that it's more complicated because there's n distributions instead of one distribution. I did actually write out the whole proof for you if you want to see it. As you can see, it's kind of long. It starts on page 9 and ends on page 11. It's not difficult, but it's just a lot of steps. But think of it intuitively as like what we did for two distributions. We're doing kind of like a test, bounding the testing error. It was very simple there. It was a Neyman Pearson test. Now it ends up involving likelihood ratios of a bunch of things and so on. But so it's not necessary to go through the proof if you don't want to. But if you want to, all the steps are there, and although it's lengthy, there's nothing too difficult there. What I want to concentrate on is how to use this result. because this, what I'm about to show you, is sort of the most common use of all of these things. Let me just check. Yeah, I'm going to put the n here. We do want the n. So that's missing in the notes. I would put that in because when you go to use this, you're going to use it for n observations, typically not for one observation. All right, so what I want to do now, probably the rest of the class, is mainly going to be showing you how to do this for regression finally, or density estimation. Yeah.
Just a quick question about that end. So where is the assumption that little n equals 1 in the proof, for example, that we?
There's no condition. I think I'm.
Because we do have like let x looks like there are little n observations.
Did I? I said let x1. Yeah, then in that case, it is. I'll tell you where it is. Although I said that, if you look into the proof, you'll see I didn't use the product measure. I used the single measure. So I stated it as if it was for n, but the proof only did the n equals to 1 case. You know that the KL distance, right, for P, for P, the product measure of P based on n observations and Q based on n is n times K. So you can always do the proof for one observation and multiply everything by n at the end. And I just sort of forgot to do that in the condition of the theorem.
Question. So in order for the average KL divergence to be bounded, do we need to require P0 and the P1 to Pn, they are equivalent, or is one direction enough?
That's the assumption of absolute continuity.
Yeah.
Otherwise, it would be infinite.
I mean, it should be two ways.
No, you only need it in one direction. In fact, the truth is, the theorem as stated by Sipikoff doesn't even assume absolute continuity, and it's stated more generally. So I just simplified things by assuming everything was absolutely continuous. Yeah, by the way, this, I keep referring to this. I think I've referenced Sipikoff's book several times. It's a fantastic book. If you want to see a lot more detail about this stuff, it's another Springer book, so you get it for free. It's called something like Introduction to Non-Parametric Inference. And so a lot of the gory details are in there, but he's a very good writer. So he has all these details about these minimax lower bounds, upper bounds, and so on. You can get a lot of inference. It's a slim volume, but it's packed with a lot of information. And you'll see when you look at the theorem I'm giving you, it looks a bit different in the book because he's doing a more general version. If you should look at the book, which I encourage you to do. All right, so we've got all the tricks we need now. Now, the rest of your life, if you have to solve minimax problems, you're in good shape. Because these are most of the tricks you'll need. There's just one more, okay? There's one catch here, which is when we go to apply Fano or Sipikoff to a function estimation problem, there's a small problem that arises. And let's think about how we're actually going to apply this now. So let's take non-parametric regression. We did this under, for example, a Lipschitz condition at a point was one example we did. But the way we're going to create these set of distributions is by, again, creating a set of regression functions. Every regression function is going to define a distribution. Maybe we'll take this to be, say, normal. I'll take this to be uniform, or sometimes we even take them to be fixed to simplify things. The key is that you have to pick different regression functions. So we have to pick an M0, an M1, an Mn. How do you construct them? Well, M0 we usually take to be the zero function, just for simplicity. Then every one of these other guys is going to be some perturbation of M. So what we're going to do is divide, say we're on 0, 1. We're going to divide this into pieces. And we're going to add little bumps. Remember we added like a little Lipschitz bump when we did the other one. More generally, we're going to add a bump like this. But we have to decide at each point, or at each little interval now, do we add a smooth bump or not? So you can think of there as being a binary sequence here, 0, 1, 1, 0, 1, 1, 0, 0. So and 1 means I put a bump, and 0 means I don't. So there's one of my functions in my class of functions. Everywhere there's a 1, I put a little bump, otherwise not. And if I call the number of, let's say I have 1, 2, up to, say, m, little intervals here, you can see that creates my set of regression functions. How many of them are there? As many as there are binary sequences. So what is n here? What is the number? 2 to the m, right. So there's kind of a tuning parameter we get to pick, which is how many things to choose here. And once I have these 2 regression functions and this whole set of regressions, for every pair, I need to compute 2 things. What's the Kullback-Leibler distance between the corresponding densities? That's just a bit of calculus. I have 2 distributions. We did it last time for one example. But I also have to compute the distance between the corresponding, let's call it m0 and some other m in here, mj, which let's suppose we're doing L2 loss. Okay? What's that going to be? Well, you can see every empty interval, it's 0. And then there's going to be some distance over here times the number of places that there's a 1. So this is going to be some number within each bin. Like when I integrate this over a bin, I'm going to get a number. I'll call it a squared, times the number of 1s. More generally, if I take any 2 guys in here, if I look at, say, the distance between mj and mk, I'm going to get a squared times the number of each one of these guys corresponds to a bit sequence of 0s and 1s. Every time they differ, every time they're the same, the distance is 0. Every time they differ, you're going to get that integral over that little bin. And what's that? That's called the Hamming distance. That's the Hamming distance. If I call the bit sequences, so let's write m0 has a bit sequence omega. So it might look like this. This is just telling me again, no bump, bump, no bump, 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 and so on. And if I have that's say mj. mk, any other function, has a different one. Let's call it, did I call it something? Let's call it omega prime. Has a different bit sequence. And when I take the L2 distance, any bin where they agree, it's 0. Any bin where they disagree, it's a positive number, times the number of places where these 2 bit sequences differ. That's called the Hamming distance. Is everybody with me? In principle, we're now ready to do Fano's inequality, because all I do is apart from how to pick the function and everything, I have the scheme ready. I've generated this large sequence of functions. This large collection of functions are a corresponding set of probability measures. I just have to check the Kullback-Leibler distance. But then what is the minimax risk? Assuming that I've satisfied that Kullback-Leibler condition, we saw that the minimax risk was bigger than s over 16. But what's s? S is the smallest distance between any pair of these functions. The difficulty with just applying Fano's inequality is there's going to be some functions in this pair that only differ in 1 bit, that have a small Hamming distance. Those are going to be really close together. That's going to make this s very small. So if I have something that looks like this, it's, 0 everywhere, and this one just has 1 blip, the L2 distance is going to be very small. And this construction is called the hypercube construction, because you can think of every bit as a point on a hypercube. Think of the coordinates of a hypercube are either 0, 0, 1, 0, all the possible different points form a hypercube. So this is called the hypercube construction. The problem is, if you think about the hypercube, there's a lot of points on the hypercube that are pretty close together. Not the best drawing, but these are different bit sequences. And some points on the hypercube are far apart, like 1, 1, 1, 0, 0, 0, and 0, 0, 0, 1, 1, 1 are far apart. That's good. But there are always going to be neighbors that are close together, too. And those ones, because we have to take the minimum, remember, S is the minimum distance over J and K between these functions, that's going to be really small. So Fano's inequality or Sibikhov's method is not going to give a good lower bound still, unfortunately, until we do one more trick, which is, think about it this way. Can't I take that hypercube and pick a point and then throw away all the guys that are too close to him? Now pick another point and throw away all the guys that are too close to him. And so keep pruning. In other words, I can do a pruning operation on the hypercube. Is it possible for me to prune the hypercube in that way and still keep a large number of functions? To get a good bound, I need a large number of functions. But I don't want them to only differ in one bit. I'd like them to differ in a large number of bits. And the answer is yes, you can do that. The proof is exactly what I just said. It's called, I'm on page 12. This is called the Varshimov-Gilbert theorem. All right? And did I write maximum? Where is that?
Page 9.
Page 9. Uh-oh. That's a typo. Thank you. That's very important typo. On page 9, I wrote maximum as its minimum. Very, very important. This would have been much easier if it was maximum, but unfortunately, proof doesn't work. We have to guarantee whichever pair we're talking about that they're a certain distance apart. Thanks. Switching that max and min makes a big difference. So here's what the Varshimov-Gilbert theorem says, exactly what I was just hinting at. I just realized, unfortunately, I've used n here slightly differently, but let me say what the theorem says. I said, consider the set of all binary sequences of length. Now, I called this length in my notes W1 to Wn, which I now realize was a mistake because I already used capital N for something else, which is the number of distributions. So to avoid confusion, let's change that to M. I don't want, these are two different things, right? The number of distributions, in fact, the number of distributions is 2 to the M. So just so I don't confuse you, I hope I'm going to change from the notes and just call that M. These are just binary sequences that we've been talking about. Okay? Okay, and here's what the theorem says, that I want to choose, so I know that how many guys are in here? We know there's 2 to the M guys in here. The question again is, can I pick a subset of these guys where the number of guys in the subset, let's call the subset omega prime, is almost as big as this, but where the Hamming distance is always big between each pair? And the answer is yes, there exists omega prime such that the following is true. First of all, it's handy if we have the 0 guy in there, because we often use that. So yes, this is in here. That's the first property. The second property is that it's almost as big, that the number of guys, the number of vectors in here, it's not 2 to the m, but it's 2 to the m over 8. So it's still exponential in m. So we haven't reduced the number too much. But the key property is that the Hamming distance between any 2 guys, for any 2 guys, omega j, omega k, and omega prime, instead of being 1, which it could have been as small as 1, it's actually at least m over 8. It's of order of m. Okay? You can look at the proof. It's very similar to what I just said. You pick a guy, you throw away the guys nearby, you pick another guy and throw the guys away nearby, and so on. And you end up with this construction. So I call this the pruned hypercube. I don't know if there's an official name for it, but that's what I call it, the pruned hypercube. So this is kind of an important technical point, which is when you're going to construct these functions for doing minimax bounds, you have to prune the hypercube. You don't use all the possible perturbations. But the cool thing is that now when I do this construction, this can't get as low as 1. This is at least a squared times m over 8. So now we have every element we need to apply Fanow-Sibikoff, which is we divide it up. We haven't decided how many things to divide it in yet. The number of guys, we form these things and we prune it. The number of guys is now 2 to the m over 8. And we have to figure out, we pick a smooth function so that we stay in our class, and we have to actually compute the L2 integral of that. That's usually not too difficult, or at least bound it. Similarly, we now have to compute the KL distance. It's just calculus. That's usually not too difficult. And then we just have to choose all these parameters, namely m and the height of the function, so that we satisfy that KL distance. So I want to do that now in an example, in the regression example. These give you the proof outline. I'm not going to go through all the calculus, but I'll give you the proof outline of how we get the standard rates. So this is our example 15. This is our standard regression example. I wrote it down somewhat generally. We'll take y equals m x plus epsilon. We're going to take m to be the set of all functions, set of all m. I'm going to write out a little bit more specifically here on the board. We'll take it to be that, for example, the let's say the beta. So this will be, that's the beta derivative is Lipschitz. The beta minus 1 derivative is going to satisfy a Lipschitz condition. Let's say less than x. Okay, so in other words, if beta is equal to 2, which is the most common case, I'm just saying the first derivative is Lipschitz. It's like saying almost like there's a second derivative. That's our measure of smoothness. And we're going to construct, we're going to use exactly this construction. And by fooling around, lots of trial and error, you have to figure out, how many bins to chop it up in. And people have done this just by fooling it around till you get a good answer. And I'm just going to tell you what the right construction is. So this is part of the art, right? You have a vague idea now. You have to create these functions. How many bins do I use? How big to make the functions? You have to try, it's trial and error. But luckily, we know what it is. It's take m to be constant times 1 over and then here we're going to add this little perturbation function. This perturbation function, I called it phi j, which is simply, so what I'm doing is, this is the first bin, second bin. So in the jth bin, I'm going to put basically a little kernel centered at the center of that little bump, which is, after all, a kernel. A little kernel centered at the center of the bin. So the way I wrote it in the notes is that that function is L times h to the beta times any very smooth kernel centered at the center of the bin. So we're kind of using kernels, but we're not doing it for estimation. We're using it for theory. The choices I had to make here were how high to make the function, and that it turns out h to the beta and L is what's going to give us the right answer at the end. In particular, it's h to the beta. You could leave this as an unknown quantity and then at the end try to solve for what you need to choose to make the KL condition hold. And similarly, this is the other free parameter, how many bins to do. And so now you can check that if I do the L2 distance, so this will be the L2 distance between any of these two functions. I called them m omega and m nu corresponding to their bit sequences. This is the L2 distance. That is, as we just saw, actually, I guess I did it on the square root scale. What is that? It's the integral, it's the Hamming distance. I guess I'm working on a square root scale here. So it's the Hamming distance times the L2, or this, which it's not hard to see, turns out to be LH to the b plus a half. I'm just integrating a little bubble, right? So it's getting the L2 integral. So therefore, well, let's fill this in. We already know this is bigger than or equal to. That was m over 8. By the way, h here is just 1 over m. And this is L, and this is h to the beta plus a half. But this is 1 over 8. M is 1 over h. So we get, at the end, some constant, just go like this, times h to the beta. Right? Because this is 1 over h, and it's the square root, so it cancels out.
Does the kernel function take 0 value outside of the interval?
Yeah. So we're choosing a kernel. We're choosing a smooth function, which satisfies whatever smoothness condition we need, symmetric, and is only supported in there.
Is that x, big xj,
Let me call it little xj. It should be little xj. It's just the center of the bin.
it should not be the data?
Right, that's correct. Yeah, so it would have been better to call that little xj.
So in the Lipschitz condition, it says beta minus L here. But if beta is integral, it will become 0.
Don't worry about I wrote it out. I don't know why I did that. I wrote it out, the general Holder condition, which allows for non-integer betas. It's very confusing. Let's just stick to the one that nobody ever uses that, so I don't know why I put that there. Let's just think about beta as an integer. It does generalize, but no one ever uses that.
In the notes, you're multiplying each of these expressions by the integral over the kernel square. Is that right? Not entirely clear what that notation is.
Oh, that's just what the integral turns out to be. And there should be a square root over that. When I integrate the difference, all I get are these little bubbles. Each one is k. I'm just using the fact every one of these functions is simply equal to a bit, which is 0 or 1, times one of these kernel functions. So when I take the difference of these two things and integrate it bin by bin, you just either get 0 when these agree, or you get the kernel function squared times the h. But can you see how if we didn't have the Varshimov-Gilbert thing, this wouldn't be m, this would be 1. This would be too small. It would be off. Presumably, I don't know who was the first one to discover that, but somebody tried to do this. It didn't work out, and they said, "Oh my God, this bound's too small. If only we could make them further apart." You know, I imagine that was the sequence that led to the construction.
Why would it be that bad? I mean, it's just h to the beta plus half or
Yeah, but it won't give you the right minimax. Right? So don't forget, we kind of know what we're aiming for here in the end, right? We want the upper and the lower bound to match. So I've saved you a lot of work by telling you the correct height of the function is h to the beta, and the correct number of bins is n to the 1 over 2 that. And you'd have to fool around a bit to see if, what would give you the tightest bound. But the bottom line is, once you have that choice, computing the L2 distance is straightforward. It's bounded below by this, and we've used Varshimov-Gilbert. And now, similarly, you can remember we computed the KL distance before. You can do a similar calculation here. I did not include all the calculations. But if we assume normal errors, it's just the difference between the means. You end up integrating across the unit interval, but you can break the integral up into pieces, and so it's a simple integral over each guy. And it turns out the KL distance between any pair of these ends up being something like h to the 2 beta. But we have to check our condition. What is the condition we require? We need that KL distance to be less than something like log n over n. Well, right? Again, I'm not keeping track of constants here, just the orders of things. Right? That was the condition we need to use, either Sibikoff's theorem or, for that matter, Fano. The difference is in Fano, you'd have to compute every pair, right? For the simplification in Sibikoff, I don't have to compare P0 and every other one. So how do I, first of all, what is n? By Varshimov-Gilbert, this was log of m to the, what was it? It's 2 to the m over 8 over n. That's like m times a constant over n. Let's make sure it agrees with my notes. Yeah. Right? But m is 1 over 8, so that's 1 over n h. So I need, what do I need? I need the Kullback-Leibler distance, which we just said has to be less than. This is always what it comes down to. There's going to be a tuning parameter, which in this case is m or 1 over h, whichever way you want to think about it. We don't know what it is, but then when we go to check the KL condition, we know that our Kullback-Leibler distance has to be less than, let's just write, has to be less than the quantity given in the theorem, which is this. So that tells us h to the 2 beta plus 1 has to be less than 1 over n, or h has to be less than 1 over n to the 1 over 2 beta plus 1. Let's set it equal to that. So verifying the condition forced us to choose the free parameter, h or m. And believe it or not, we're finally done, because what was the distance between any pair of these things? H to the beta. So the minimax risk is bigger than h to the beta, but we're forced to choose h to be this. And look at that. Now I did this for some reason, taking the square root. If I'd done it without taking the square root, which was probably what I should have done, so if I'd done squared error instead of the square root of squared error, of course I would have gotten the square of this. So I would have gotten, and that's where that famous expression comes from that we've seen so many times in the course. If you did this in d dimensions, it's pretty painful, but it's the same construction. You would have to now divide it up into cubes like this and put little bumps on the cubes. I mean, there's just a lot of bookkeeping to do, but it's exactly the same proof. And you would get Rn is bigger than 1 over n to the 2 beta over 2 beta plus d. That's why we keep getting that expression in all of our minimax rates. And as far as the upper bound goes, we saw that there were things like kernels and local polynomials and so on that achieve that rate. So we already have an upper bound. And hence, we have a theorem now that at least up to the rates, we can say that the minimax rate, I'm going to write it like this and explain what this means, is 1 over n over 2 beta plus d. This notation I use to mean, when I write an, bn, that just means that a over n and b over n are asymptotically bounded away from 0 and infinity as n goes to infinity. In CS, I think you call that theta or omega or something like that. Big theta. I don't like to use big theta because in statistics we use theta for parameters. So it would be really confusing to use it. Plus, it's kind of a symmetric condition. So I don't like writing this is theta n of this. I don't know. Somehow it doesn't seem right to me. So I like this better. Anyway, it means that we don't know the minimax rate exactly. We don't know the constants except in very special cases. But we do know the rate of convergence. You can't beat that rate of convergence. And we know things that achieve it, like local polynomial estimators and so on. So that's a pretty complete story about how we get these minimax rates. I went pretty fast. But if you should ever need to compute one, and you never know, you may be writing an IPS paper, and your advisor says, what's the minimax rate in this problem? I know how to do that. And you just look back at the notes and see how it works. And once you've done it a few times, you know what the steps are. It may be non-trivial to figure out in a hard problem how to pick the functions and so on, but at least the strategy is always basically the same. You construct some finite set of things that are kind of hard to tell apart but well separated. So I hope that at least gives you a feeling for how these minimax things are constructed. It's quite different than how we did it in 705 for parametric models. And we could do the density estimation case. It's done for you later in the notes. It's pretty much the same construction, and you get similar rates and so on. I am going to mention a few more examples, but let me just pause, because I know there's a lot of little pieces here, right, that went together. So let me just see if there's any questions about what we did. Everybody okay? All right. I have to tell you, many times in the past, I've had students who've taken this course and then ended up writing lots of ML papers where they went ballistic computing minimax bounds and did really, really, really complicated minimax bounds. Got very, very good at it, doing very complicated problems. So it can be useful for doing theory. Now, again, it's not something, if you're more interested in just, what works and applied stuff, obviously computing these minimax bounds is not something you're going to spend a lot of time doing. But it is useful theoretically. Let's look at a few more quick examples. I don't want to, these aren't examples where I'm going to do the calculations. I just want to show you some things that people have learned by computing minimax bounds. The first one is we should return to parametric models. In general, a good rule of thumb is that in well-behaved parametric models, the minimax risk tends to behave, I'll do this, like 1 over the square root of n. And how do we show that? So I'm going to show you the easy way of doing that. For completeness, I actually put in page 14 what's I believe is the most general theorem about minimax estimation in parametric inference. It's called the Hayek-Lacombe theorem. You can stare at that for a while if you like. It's a very, very complicated looking result, but it's very general and very precise. It's I just put it there because it's probably the best available result. But that's just there for your information. I'm going to show you a simpler, less precise argument to say, at least in well-behaved parametric families, why do we expect the minimax rate to be like 1 over n, or in terms of squared error, 1 over n? And notice, by the way, the difference, right? So if this is the expected value of theta hat minus theta. I'm saying is something like 1 over root n. Or if I'd squared it, it would be 1 over n. Notice that the parametric rates are always slower, 1 over n, 2 to the beta over 2. That's because non-parametric inference is harder. Notice, however, what would happen to that rate as beta goes to infinity? You get back the parametric rate, 1 over n. If you have infinite smoothness, it's behaving now like a parametric model. But here's a quick rough derivation of why this is true. Let's just do it on the real line. So I'll pick a point theta, and I'm going to pick pick another, let's call this theta 0, I guess, and theta 1. And I'm going to pick theta 1 to be equal to theta 0 plus 1 over root n. Now I'm going to use Lacombe's lemma. So the risk should be that distance, which is 1 over root n, divided by 2 or something, but I'm using my squiggle here, which means I can throw away constants, times e to the n times the KL distance between p theta 0, p theta 1. But at some point, we talked about this, maybe it was even a homework question, that in a well-behaved parametric model, what do we know about the KL distance of two parametric distributions that are close together? I think this was a homework question in 705. Or maybe I talked about it either on the board or it was a homework question. Anybody remember what is, if I have two parametric distributions, smooth distributions that change smoothly when theta changes, and I compute the KL distance, do you remember we had a result that this was approximately equal to? Well, I'll remind you, it's the squared error, it's the squared distance between these two things, which is 1 over n, times the Fisher information. You can see how this depends on the model being a nice model. So for example, the Fisher information has to exist and be not 0 and so on. So now we can plug that in here. This is 1 over root n times e to the n over n times I of theta. This is now, assuming, again, this is well defined, this is just a constant. So there you go. There's our minimax lower bound of 1 over root n. Or if we'd done squared error again, if you prefer squared error, that would be 1 over n. If you did it in d dimensions, a d-dimension parametric model, you would simply get d over n. So you can see how parametric problems get harder as the dimension gets bigger, naturally. So we're not getting the constants and all that, but at least in terms of rate, we can easily use Lacombe's method to get a minimax bound. Let's look at a few other examples. So for your interest, I'm not going to go through it. I did density estimation at 8.2. We get back the same rate. I only did it in one dimension. And just for fun, I did it using a different loss function called Hellinger loss, but it doesn't matter. You get back the same rate. So I'm not going to do it. It's exactly the same calculation we just did for regression. You just chop it up into pieces and so on. But it's there for you to look at. There's a few other ones I put in just for, for your information so you could see them. I wanted to just highlight a couple of cool ones. I think there's one or two very cool and surprising minimax bounds. These are meant to be examples where the answer is surprising. Okay, these are surprises. At least I thought they were surprising. So it's an example where minimax thinking helps to reveal something theoretically about a problem that maybe wouldn't be expected. So if you look at the table at the top of page 19, this is from a paper by my colleague Arti Singh and her colleagues. And it's about something called semi-supervised inference. How many of you are familiar with semi-supervised? Oh, OK. Let me tell you what semi-supervised learning is. Semi-supervised learning, it's kind of a cool idea. Suppose I gave you, well, here's an extreme example. I'm going to do classification, all right? And I only have 2 data points, a 1 here and a 0. It's not very much information to go on. And now I ask you, where's the decision boundary? Where might you put it? Well, you could put it here. You could put it here. There's a lot of places to put it. But what if I have some unlabeled data too? After all, if I think about downloading images from the web, and I pay a graduate student, can you classify these as cats and dogs? But I don't have a lot of money, so I can only, maybe I download 1 million images. I realize I can't pay this guy to classify 1 million images, so I'll pick 10 at random, classifies them. But the other ones are still there. I have all this other data, but they're unlabeled. So suppose the unlabeled data look like this. In fact, you might imagine maybe having a few more labels, like 1 and 0. Somehow, if you see these unlabeled data forming these nice clusters, intuitively you would think maybe I could draw the decision boundary like that. Somehow it feels like the unlabeled data can help you even though they don't have labels. It seems kind of counterintuitive. No labels, and yet it seems like they could help you. When you first hear about this, you should think it's impossible because these other data are like missing at random. How do they have any information? Well, it is impossible unless you make further assumptions. The extra assumption you need, which is sometimes called the cluster or manifold assumption, is roughly speaking that if you think about what the regression function looks like, there's got to be sort of clusters in some sense in the data, first of all, and the regression function has to be kind of relatively smooth over the clusters. So that the fact that it's kind of smooth over here means that since I got a 1 here, 1 here, I'm likely to get lots of 1s here and likely to get lots of 0s there. But also, if these clusters are too close together, that's not going to help me too much. On the other hand, if they're really far apart, probably I don't even need the unlabeled data anyway. And there was a big mystery in the field a few years ago. Well, it seems like a few years ago to me. Let's look at the date of the paper. 2008, because I feel that until their paper was published, I feel this was an unsettled question, which is people had this intuitive idea of doing semi-supervised learning, and people were using it, and it seemed to work sometimes, and it seemed to not work sometimes. Why? Why was it working? Why was it not working? And what this paper did was a very, very nice theoretical Minimax analysis, finding the upper bound on any semi-supervised method, which means a method which gets to use the label and unlabeled data, and a lower bound on any supervised method which ignores the unlabeled data and says, when does one beat the other one? And what they found out was it's quite delicate. I have a chart here, and the important thing is there's different regimes here, which, roughly speaking, these different regimes correspond to how close are these clusters together and how much smoothness is. And what they found was the important thing to notice is simply in certain circumstances, you get a better rate from semi-supervised learning. Those are the ones that say yes, but in some cases you don't get a better rate. And the importance here is not that it changed anybody's way of doing semi-supervised inference, but I think it was theoretically important that it gave a kind of crisp answer to why semi-supervised inference helps, or more importantly, when does it help? And the tool here was to do these minimax bounds on the error rate. So I just like to use that as an example where I feel like there was a lot of confusion in the field, and there was papers claiming different things and so on, and I feel that it was by doing that Minimax analysis that they really nailed the problem and sort of cleared up what was going on. Okay, here's another one of my favorite Minimax stories, which is very surprising to people, and often very disturbing. Actually, let's do two versions of this. We'll do the density estimation version and the regression version. And I see people actually handling this in practice often incorrectly. So let's start with the density estimation version. Let's suppose I have x1 to xn is from a distribution p. P has some density p. And if we assume the usual smoothness conditions, we're now experts on minimax theory, and we know we can construct a minimax rate. It's going to look something like, let's say it's one-dimensional, so it's going to look like this. Okay, so now, we have an idea how to do the minimax lower bound. We know something like maybe a density estimator, or a kernel density is going to achieve that bound. Great. But here's something that happens a lot in practice. Sometimes you don't get to observe the x's. Sometimes they're measured with error. So sometimes what happens is you observe, let's say, zi equals xi plus epsilon I. And let's take epsilon to be, let's say, some sort of normal 0, sigma squared. This happens a lot in science. You're trying to measure something, but there's some measurement error. You don't get to measure it exactly. The question is, now if I only have access to the z's, but I want the density of the x's, what is the minimax rate? And the answer was shown to be, I guess it was in 1991, was shown to be 1 over log n to the beta. Which is, log is, to me, is like a constant. You know, that's really slow. That's for all practical purposes, this isn't even going to 0. It's kind of saying you can barely even estimate the density. That's very shocking when you first see that. That just adding a little bit of noise, normal noise, you can't estimate the density anymore. And the same thing happens in regression. Suppose I have this regression model, but suppose I don't get to observe the x's. Adding error to the y's doesn't matter, right? Because if you add error to the y's, it just becomes part of the epsilon. You still have the same regression problem with just bigger noise. That's quite different than adding errors to the x's. Suppose, again, that I observe zi, but I don't get to see these x's. Now, if all you care about is pure prediction, it doesn't matter. You just now predict the y's from the z's, and you're back in the usual prediction problem. But suppose you're actually interested in the relationship between y and x, you know, some scientific problem. You want to understand what is the relationship between y and x. So if I'll draw a graph for those of you who know graphs. It looks like this, right? We have x, y depends on x, z depends on x. I circled x because we don't get to see x. But we're interested in this relationship m between these. And the answer, again, is the best rate you can get is logarithmic. And I've seen a lot of people in sciences and actually in machine learning not realizing that when the x's have error, it's not the same as just having extra error in y's. Everything changes. You can't estimate. You basically can't estimate m anymore, at least not very accurately.
So this is actually seems pretty intuitive. So am I interpreting this correctly that the magnitude of the variance of our noise is just going to make a constant difference?
Yeah, I'm assuming the noise is just some fixed small constant here. If that went to 0, you'd be fine. But then you don't have measurement error anymore. So I find this very surprising. I don't think this is something you would guess. In fact, here's another interesting question. When it comes to adding noise, how does the distribution of the noise affect this rate? And it turns out the normal case is the worst case. Usually normals are our friends, right? We love the normal distribution. The normal is the worst case. That's where the log n comes from. If you actually had other distributions here, you get slightly better rates. So normal noise actually is the worst possible case for measurement error. So this, to me, is another example of where doing minimax analysis was very revealing. In fact, people came up with estimators before anybody ever did minimax analysis, and they started noticing, wow, my estimator is doing really badly. Why is it doing badly? Then they computed the bias and the variance, and they said, oh my God, it's converging at this rate 1 over log n. Maybe I can do better. And then no, the minimax analysis said, no, that's the best you can do. There's no point trying to construct a better estimator.
So is this related to the entropy maximizing properties of the Gaussian?
No, it has to do, all the analysis in this case is done in the Fourier domain. And it has to do with the properties of the Fourier expansions of the distributions. So it's, yeah, the analysis here, the minimax is kind of quite a bit different from the way we did it here. You have to switch to the Fourier domain and so on. And the estimators involve something called deconvolution. So it's kind of a complicated story. But the message is simply that a small change in the model can have a profound effect. And through minimax analysis, again, what we see is that this is unavoidable. It's not that there's something wrong with the estimators. This is the best you can do.
But normally, we always have some error in the observation.
Well, if you don't, so let me be clear. If you don't care about estimating m, if all you care about is predicting y from z, it doesn't matter. You still might predict well. But if you really want to estimate m, and if there is some error, you've got a problem. Yeah. But you're right. It's very common that there's error, and people tend to ignore that. But it actually matters. What's the difference between predicting and estimating? Well, if I just want to predict y from z, it's possible I could do that even though I can't estimate m well. After all I care about is the relationship now between y and z. What's going on between here and here might not matter to me. So it's conceivable that I could predict well even though I can't estimate this relationship, this function very well. The function estimation problem, so if there wasn't measurement error, the function estimation problem is about the same difficulty as the prediction problem. When there's measurement error, the function estimation problem is very hard. The prediction problem still might be doable. I'm not saying it's guaranteed, but it could be.
But I mean, estimating some other m prime from 0 to 1.
If implicitly what you're doing is looking at the marginal graph, and there's a new regression function g that you're estimating. That's right. Yeah.
Does this kind of result also carry over to the parametric case, or like,
Yeah.
or is it that when you restrict it?
The parametric case, the rates aren't as bad, but it definitely hurts your estimation.
So in this sense, the RA is actually defined over the at the estimated G value. So the RN,
Rn is defined over we're looking at, you're going to come up with some estimator, and I'm going to compare it to the true. So I'm assuming you're interested in estimating the relationship between y and x. And that's what makes it hard, because you don't observe x. You're observing some sort of surrogate for x. How are we doing on time? Okay, I'll mention, any other questions about that? I just wanted to mention a couple other, these are sort of all in the realm of interesting tidbits. I mean, you know, sometimes we have a whole course on minimax estimation, an entire term. I mean, you can see how it's a very rich area, and you can spend a long time on it. So I just wanted to get across what I consider the basic construction and then tell you some of these interesting examples. Let's see. So there's, you know, you should consider all of this sort of optional reading, but there's in section 8.8, I wanted to give you some examples where the minimax risk can be determined exactly, up to constants even. There's a famous theorem called Pinsker's theorem. Which basically is the following problem that you have x1, let's say x1, they're all normal, it's the normal means problem. So we have, well, the way people usually write it is this, xj is equal to theta j plus 1 over n epsilon j. You can think of this as already, I've taken a sample average, and I have a whole bunch of sample averages. So j here is 1 to n. But because they're averages, that's why the variance is like 1 over n. And you can ask, how well can you estimate this? And you notice on the homework, I gave you a condition like this, j to the 2p. Actually, in this theorem, I think I took p to be, yeah, like 2p. Constant. That corresponds, why did I put that there? If I think of a regression problem and I expand it into a basis, and if I told you that function was in a Sobolev space of order p, that corresponds to having the regression coefficient satisfy this condition. That's why I put that condition there. And in this problem, if you just simplify it as pretending you're estimating a bunch of normal means, not only can you get the usual rate, which we know is 1 over n to the 2 beta, or 2 beta plus 1, but we can actually get the constants in front because of normality. And that's what this complicated expression there is just showing you. I just wanted to show you an example where the exact constants, they're called the Pinsker constants, are actually known. You know, I'm not going to go through it, but there are cases where more than the rate is known, but they're pretty special cases. It's pretty hard in general to get those constants. All right, what else can I tell you that's interesting? Did the constants matter? Only if you're a real aficionado who loves this minimax theory. It depends who you ask. I mean, guys who spend their lives working on minimax theory would be horrified that I just made light of that. But in general, the constants are not usually so important. And maybe the last thing I have time to mention is you might wonder, is there kind of a general way to figure out these minimax bounds? And roughly speaking, there sort of is. If I give you a kind of arbitrary set of distributions, and I put a metric on these distributions. This could be like total variation distance or some other distance. We talked about Hellinger distance at one point. Remember, there's different distances between distributions. And do you remember when we talked about concentration of measure? We talked about this thing called the covering number. How many balls of size epsilon does it take to cover the space? In this case, it would be how many balls of size epsilon in this distributional distance. Then, under certain conditions, it turns out you can always get the minimax rate under these conditions by taking the following equation, which is known as the Lacombe equation. You solve this equation. It's magic. You take the log covering number, set it equal to n epsilon squared, and solve. And the solution, it's going to depend on n, under certain conditions is precisely the minimax thing. That's a kind of unifying way to think about minimax theory. And why does this happen? The reason is, I actually have the proof in here. Again, it's optional if you want to go through it because it's quite long. But the basic principle is pretty simple. Here's how it works. Once I cover the space with a finite set based on this covering number, and you apply Fano's inequality. That will give you a lower bound. We just saw that, right? And the upper bound, roughly speaking, is I'm just going to do maximum likelihood over that finite set. And that gives you the upper bound. There's quite a few details I'm leaving out. But that's the essence of the story. And so this equation is sometimes used as a way to get minimax rates in lots of problems. And I just want to mention it because I know it seems like every single problem we do, you have to solve it separately and think about how am I going to solve this problem, which is unfortunately true. But this one little picture here at least gives you some sense that the complexity of the model, which is governed by this number, the covering number, which also came up in concentration of measure, is going to affect the minimax rate. The more complex it is, the worse the rate's going to be. I think I even recorded, did I write down the covering numbers? I thought I had made a little chart, but I guess I even, if you're interested, on page 28, I took a bunch of common spaces, and this log n epsilon is sometimes called the entropy, which is a bit confusing because it's not entropy like you know from information theory. It's called metric entropy. And all I did was I listed a bunch of common spaces. People have worked out what this covering number is, so I listed the entropy. Then I solved the equation, and you get these rates. And so you can just read off the minimax rates in lots of problems. All right, so that's, once again, in the realm of extra material that you don't really need to know. For doing the homework, if you can just sort of do Lacombe's method, that's kind of good enough. Just the basic thing. I don't expect you to be experts in minimax theory, but I did want to give you a kind of overview of all the different stuff that's available.
Because it seems like so simple or something.
I'm sorry?
I mean, is there a catch with this?
Is there a catch with this? It seems too simple. If you look at the theorems, there's some conditions on the sets of densities. They can't be completely arbitrary. And also, I'm assuming the loss function we're interested in is sort of something to do with the distributional distances between these, which may or may not be true. So yeah, so it's not completely as general as I'm making it sound. All right, so that's hopefully I gave you a taste of Minimax theory without overwhelming you. So I was thinking about what to do next. So the next thing I think was going to be density estimation, but I realized we did density estimation, I think, in 705, right? We did kernel density estimation. I don't see any point in redoing it unless there's some sort of outcry. You know, we're all happy with kernel density estimation and all that. Because I thought what I would do is I put the notes up for you, by the way, they're there. And you can look at them if you want, but I just felt like we've already really seen that in 705, and it's very similar to non-parametric regression. So I was going to go on, do some other things. I think the next topic is non-parametric Bayes, which we didn't do that in 705, did we? I start to lose track of what I've taught in which class. So I thought I would cover maybe the next topic would be non-parametric Bayesian inference, because that's getting a lot of attention these days. And then maybe clustering after that. I haven't really decided. Does that sound good? All right. Any other questions? All right, good. So then we'll see you next week.